Last time we started with Nash equilibrium. We'll be continuing with that and we'll apply that concept to few other games. In the last class, if you remember, we've done Nash equilibrium in Prisoner's Dilemma. Today we'll try to see which is the Nash equilibrium in Battle of Sexes game. So again, in the Battle of Sexes, if you can recall it, two players, player 1, player 2, they have two possible sets of action, going to movie or say a game. Again, for player 2 also, movie or game. And the idea is to spend the time together in their class, to spend the time together in the evening. So its payoffs are something like this. So we'll be applying the Nash equilibrium concept here. So we will see what is the best thing for player 1 to do if player 2 is choosing M. If we look at that, the best thing for player 1 to do is to play M if player 1 is choosing M. If player 2 is choosing G, the best thing for player 1 to do is to choose G. If player 1 is choosing M, the best thing for player 2 to do is to choose M in this row. If player 1 is choosing G, the best thing for player 2 to choose is G. So this and this. These two are the Nash equilibrium of this game. So a game can have one Nash equilibrium, it can have a multiple Nash equilibria, or it may not have any Nash. Battle of Sexes has two Nash, Prisoner's Dilemma had one, and we'll look at another game in which there will be no Nash. So in this there are two Nash. First of all, the player 1 choosing M and then player 2 also choosing M, that's one Nash, and the other one is player 1 choosing G and player 2 also choosing G. So both of them are Nash or they both have steady state equilibrium. Next we move on to another game which we've done earlier, which was the matching pennies game. If you have your books with it, it's figure 19.2 in the book again. We can go back to that and let's see. In that, if you remember, two people are tossing coins and player 1 is winning if the same side of the coin shows. Player 2 is winning if opposite sides show. So either it can be head, tail, tail. If same side is showing, that means if heads show on both the coins, player 1 will get ₹1, player 2 will pay ₹1, so his payoff is -1. And likewise, if the tails is showing, player 1 is receiving ₹1, player 2 is paying ₹1. And likewise for player 2, if opposite sides are showing, that means heads for player 2, tails for player 1. Then player 2 is winning, he is getting ₹1 from player 2, so -1 for player 1, +1 for player 2. Likewise here also. So now if we look at a Nash for this particular game, we will see that this game has no Nash at all. For example, if player 1 is playing head, the best thing for player 2 to do is, for him is tails. If player 1 has got tails, the best thing for player 2 is heads. So if we write it, mark it like this. Likewise for player 1, if it's heads for player 2, the best thing for player 1 is heads. If it's tails for player 2, the best thing for player 1 is tails. So there is no Nash in this particular game. So that means there is no steady state equilibrium in this game. So as we were talking about, it is not necessary that every game will have a Nash. Next we move on to the stag hunt game and just see what kind of Nash we get there. Since I'm doing it with a payoff matrix, we'll be using the two-player version of the game. You can read the book for the multiplayer version also. So it's figure 21.1 in the book. So two options, either to go for a stag or to deviate and go for a hare, go for a stag and go for a hare. If both players go for the hare, the payoffs are 3-3 for both. If both go individually, or you can do 2-2 the way book is doing. If both play hare, then it's 1-1. If player 1 is playing this, and then this was the matrix that we've done earlier. In this particular game, again, we can see the Nash hare. If player 2 is playing stag, then the best thing for player 1 to do is to play stag. If player 2 is playing hare, the best thing for player 1 to do is to play hare. If player 1 is choosing stag, then the best thing for player 2 to do is to play stag here. If player 1 is choosing hare, the best thing for player 2 is hare. So the key here is to look out for those blocks where both the payoffs are underlined. So here both the players are underlined, payoffs are underlined here, and both the payoffs are underlined here. So this is one Nash, this is another Nash. So in this game also there are two Nash equilibria. One is stag stag and the other one is hare hare. But if you look carefully in this particular game, this Nash is giving a higher payoff to both the players as compared to this Nash. So one can say that this particular Nash is inferior to this Nash, but it is possible, it is plausible. So we can't say that this can never happen. This can, but this will be an inferior outcome as compared to this outcome. Okay, so there are a few other games here which you can see for yourself, and also there are certain exercises in the book, and I think your readings should have the solution to all those exercises also. So please continue to do those exercises also. Next, we move on to something that we've not considered so far, concept of strict and non-strict Nash equilibria. So strict and non-strict means the definition, if you remember the previous definition of Nash that we've done, the definition 23.1 in the book, requires that only that the outcome of a deviation is no better for the person who's deviating than the equilibrium outcome, and then it's a Nash equilibrium. That means a person deviating from Nash equilibrium will be at least as good or as good as with the Nash than with the deviation. So that means by deviating, the person cannot attain a higher payoff. That was the only definition that we've done so far. But some games have equilibria in which a player is indifferent between her equilibrium action and the other action, given the other player's action. So let's do an example to understand what we've said here. We are doing a particular game here where one player has 3 actions and the other one has 2 actions. So it's again an example from the book only. It's figure 33.1 from the book. Player 1 has, say, 2 actions, say T and B. No particular theory behind or story behind this particular game. Player 2 has 3 actions, L, M and R. They're just simple alphabets denoting their actions. And let's write the payoffs now. This particular matrix will have 2 rows and 3 columns. So far we've done symmetric, where both the players had same set of actions. But that is not a necessity. So let's say the payoffs are something like this. So we'll just again mark the Nash equilibrium here. So going for player 1 first, if player 2 is choosing L, the best action for player 1 is T and B both. If you look carefully, if player 2 is chosen L, then we are in the first column here. If player 1 plays T, the payoff will be 1. If player 1 plays B, the payoff is again the same. So situation where player 2 has played L, actions T and B are giving same payoff to player 1, which implies that player 1 will be indifferent between playing T and B. we go to the second column, player 1 should choose T because that's giving a higher payoff. If we go to the third column, player 1 should choose B. So let's do this exercise for player 2 also. If player 1 has played T, then player 1 can choose L and player 1 can choose R also. Again, between L and R. If player 1 has played T, for player 2, L and R are giving same payoff. So that means again player 2 should be indifferent between either playing L or playing R, given the information or given that player 1 has played T. For this action B of player 1, player 2 should choose M. So if we look here, the Nash for this game will be this, where player 1 is playing T, player 2 is playing L. Okay? But if you look carefully, this T and L is a Nash equilibrium, but it is not a strict Nash. When we say strict Nash, we mean that if suppose in this particular game, player 1 deviates from his Nash strategy of playing T and he plays B rather than T, then player 1 will not be any worse off because the payoffs are same. So the Nash equilibrium strategy of player 1, which is T, is not making him any worse off, but he is indifferent between the Nash strategy and the non-Nash action here. So that's why this particular Nash equilibrium is not a strict Nash equilibrium. So to give you a formal definition here, an equilibrium is strict if for every player equilibrium action is strictly better than all of her other actions. If you look in this game, T is not strictly better than action B for player 1, because both, if player 2 has chosen L, T is giving a payoff 1, B is also giving a payoff of 1 to player 1. So therefore, T is not an action which is strictly better than B. So if we are defining a strict Nash, that will be an equilibrium is said to be strict if each player's equilibrium action is strictly better than all of her other actions, given what the other player's actions are. That means a Nash profile A star is a strict Nash. I can just drop this and write it here. A star will be a strict Nash if for all players I we have that utility of player I with Nash profile A star is strictly greater than utility of player I with other actions apart from the equilibrium action when everyone else is playing their Nash strategy. If you remember in the earlier case, the earlier definition of Nash we've written, we've had a greater than equal to sign there. That's just the definition of Nash. When we put this here, when we remove this equality, it becomes a strict Nash. When we have this, it's a non-strict Nash.